Hello guys, welcome back to CFD College. I'm Ashkan and this is another video on Fluid Mechanics 1 assignments. This video is about assignment D where we should solve 4 problems on linear momentum equation. We use this equation to find forces due to fluid flow. When we have a fluid flow, it applies forces towards, I don't know, walls. If we have a jet impinging a surface, from the jet there is a force acting and applying to the surface, and we use linear momentum equation to find that force. So first, please subscribe the channel, please share these videos with your friends if you find them useful, helpful, and if you enjoyed them. And that's it. If you have any question, you can write your question in the comment section below, and I try to answer your question as fast as possible. So this is the first problem number 38 from chapter 5. Here we have this pipe. Water flows through a horizontal bend. So we have this bend and discharges into the atmosphere. So here we have atmosphere. When the pressure gauge reads 10 psi here, so actually we know we have the pressure at this section. The resultant x direction anchoric force FAX here is 1,440 pounds in the horizontal plane required to hold the band in place. Determine the flow rate. So this time we have the force and we want to find the flow rate through the band and the y direction anchoring force. So FA y required to hold the band in place. The flow is not frictionless. Okay. So what should we do? The thing that we know is we have this force, and to find the force we should use linear momentum equation. If you are interested in learning this equation, the basics, you have to see my another video, tutorial 7 on fluid mechanics 1. I explained the equation, the linear momentum equation, in that tutorial. So in this tutorial I'm just solving these assignments. Okay, so we should use linear momentum equation. In x direction we have the force, so we should use the linear momentum equation in x direction, probably to find velocity, and then we can find Fay. So as if you have seen that video, you know that the first step is to define the control volume. So this is the control volume we should use. As I mentioned in video on tutorial 7, the control surface should be perpendicular to the flow. Here we have inflow, so the control surface is perpendicular to that, and then we should follow the walls, and here we have outflow. So again, the control surface should be perpendicular to the outflow. So here we have control surface 2. Here we have control surface 1. Why I pick this section? Because we know the pressure, and we also know the pressure at the outlet. It's atmospheric pressure. Okay, let's draw the control volume. It's like this. Here we have inflow V1, and actually we have outflow here V2. We have this angle 45 degrees. We have another force due to pressure. Why? Because at the outlet we have atmospheric pressure, but at the inlet, at section 1, at control surface 1, we have this pressure which is above atmospheric pressure. It's higher than it. So here we have force due to pressure P1A1. Actually we have another force here P2A2. Remember that the forces due to pressure are always perpendicular to the control surface and toward the control volume, whether we have inlet or outlet. P2 is 0. Why? Because we are working with gauge pressure. If instead of PSI we had PSIA here, then we should consider P2 as an atmospheric pressure, which is 14.7. But now, since pressure at control surface 1 is gauge pressure in PSI, it means that P2 should be in gauge pressure, so P2 is 0. But if, for example, it wasn't an outlet, and for example the pipe was like this, and this was another section inside the pipe, then we cannot neglect P2A2. So this is the control volume. We have two control surfaces, control surfaces 1, control surfaces 2. We have these velocities, we have this FAX, the forces, and its FAY. And now we need to define the second step was to define the x and y direction. It's easy. This should be x and this should be y. You can define it in a way that you want. For example, someone likes to define it this way. It's okay. It depends on you. Okay. Now the third step is to use and write down the linear momentum equation. So, which is in x direction first. Why? Because we know FAX. The summation of forces in x direction equals the change of momentum inside control volume plus the exchange of momentum through control surfaces. It's important. One thing that matters is here the V, the first velocity outside the parentheses, is the velocity in the direction you are solving the equation. So here we are solving linear momentum in x direction, so here we have rho Vx, and in the parentheses we have dot product of velocity dA. As you know, where we have inflow, actually inlet, V dot n equals minus magnitude of V V1 for example here, and if you have outflow V2, V dot n equals the magnitude of V2 with positive sign. And that's because here where we have inlet, the normal outward vector is in the opposite direction with respect to V. And here, oops, sorry, but at the outlet, the normal outward vector is parallel to velocity. Since we are working in a steady state, this term is 0. Now we have to calculate the forces and the exchange of momentum at the inlet or outlet. Summation of forces in x direction, we have P1 A1, which is in x direction. We have FAX in the opposite direction, so minus FAX. And here P2A2 is 0. But if it wasn't 0, you should find the value in x direction. So it's x, it's y, and this should be P2A2. Here is 45, cosine of 45. So here we should have, and it's in the it's parallel to x. We have P2A2 cosine of 45, but in this problem P2 is 0. Equals, we have two control surfaces, and control surface 1 rho Vx is V1. As you can see, V1 is parallel to x direction, so V1x is V1, and V1 dot n, since we have inlet, as I mentioned, V dot n equals minus V1. dA at control surface 2, we have rho V2 in x direction. This is V2, and this is y, and this is x. So V2 in x direction, this, oh, it's 45, it's okay. This is V2x, which is equal to V2 sine or cosine of 45 degrees. So rho V2 cosine of 45 times V dot n for the outlet is the magnitude of V2. There is no need to decompose V2 and find the component in x direction for this dot product. dA. Okay, now we can solve it. So P1A1 minus FAX equals rho minus rho V1 V1 times V1A1 plus here V2, it's negative because it's in the opposite direction compared to x, so here I should put this negative sign. Minus rho V2 times cosine of 45 degrees times V2 times A2. Yes. Okay, now we should find the flow rate. As you know, Q equals V1 A1 equals V2 A2. So from this equation we can find V1 square equals Q square over A1 square, and V2 square equals Q square over A2 square. Now if we put these equations into the main one, equation 1, what we will have is P1 A1 minus FAX equals minus rho Q square over A1 minus rho Q square over A2 cosine of 45. So from this equation you can find the flow rate. The flow rate is equal to square root of minus P1 A1 plus FAX divided by rho times cosine of 45 over A2 plus 1 over A1. And now you can calculate it because you know the values. Minus P1, which is 10 psi, pounds per inch square. You should convert it to feet square, so 144 inches square over feet square times area, which is 0.2 square feet. As you can see here, the area is 0.2 at the inlet and 0.1 at the outlet. Plus FAX 1440 pounds over rho 1.94 slugs per cubic feet. You should convert it 1 pounds per slug feet per second square, and cosine of 45 over 0.1 feet square plus 1 over 0.2 feet square. From this you can find Q. So Q equals 7.01 cubic feet per second. Now we can find FAY. We should solve the momentum equation in y direction. The summation of forces in y direction equals the change of momentum in control volume, rho v dv. This is the volume, but it's 0 since we are at steady state flow, plus change of momentum rho vy v dot n dA. Okay, let's see what we have. In y direction we only have FAY because P2A2 is 0. If it wasn't, P2A2 had a component in y direction, but P1A1 doesn't have any component in y direction. So with regard to forces, we only have FAY, but I think it's in the opposite direction with respect to y, so minus FAY equals at control surface 1, V is horizontal in x direction, so V1y is 0. So if I want to solve it, I should write at control surface 1 rho V1 in y direction is 0 times V dot n at inlet, which is minus V1 dA, plus at CS2 we have rho and V in y direction. If you see here, we have v2 in y direction, v2y equals v2 sine of 45, but you should remember that it's in the opposite direction, so we need a negative sign. Rho times minus v2 sine of 45, and v2 dot n, since it's an outlet, equals v2 dA. So this one is 0, and we can find that fay equals, we have the negative sign, so they cancel each other. Rho v2 sine of 45 v2 a2. So again, we know that v2 equals q square over a2 square. So fay equals q2. You should put this in the equation, over a2 sine of 45. So fay equals, you can do the math, 674 pounds. See, it was easy, I think. It wasn't difficult. Okay, next question. Problem number 62 of chapter 5. Air discharges from a 2-inch diameter nozzle. So here we have a 2-inch diameter nozzle. So the jet diameter is 2 inches. And it strikes a curved vane. This is the vane, which is in a vertical plane, as shown in the figure. A stagnation tube here, this tube, is connected to a water U-tube manometer. So this is the stagnation tube connected to the water U-tube manometer. Is located in the free air jet. Determine the horizontal component of the force. That the air jet exerts on the vane. Rx. Neglect the weight of the air and all friction. Okay. So we want to find Rx. We have this air jet. This is the vane. We have this stagnation tube. And we want to find the force. As you know, since we have a fluid flow and we want to find the force, we should use linear momentum equation. But first, the first step is to draw the control volume, which is this one. So if I draw it here, this is the control volume. We have outflow V2. The angle is 30 degrees. Here we have inflow V1. And we have Rx. What else? That's it. There is no other force. But we don't know V1 and also V2. Okay. It's obvious that we need to use this stagnation tube and manometer to find something. So let's start solving the problem. Then we can see what is missing and what we should do with this stagnation tube. So this was, the drawing the control volume and the forces. That was the first step. The second step is to define x and y axis like this. X is in the direction of the force, the horizontal force. And now we can solve linear momentum equation. So the summation of forces in x direction equals to change of momentum inside the control volume plus the exchange of the momentum through control surfaces, rho vx v dot n dA. This is CS2, this is CS1. So we have two control surfaces. Since we are working under steady state condition, the first term is 0. And so the only force that we have is Rx, which is in the opposite direction compared to x. So minus Rx equals over control surface 1, we have rho. V1 is in the direction of x, so it's V1. V dot n, here we have an inlet, so it should be negative, and the magnitude of velocity, which is V1 times dA, and over control surface 2 we have rho. V2, we should find the component in x direction, so this is V2, it's x and it's y. If this is 30, here is also 30 degrees, and the component in x, which is V2x, equals V2 cosine of 30. Don't forget to put the negative sign here, minus V2 cosine of 30y, because V2 is in the opposite direction compared to x. V dot n, we have outlet, and on the at the outlet we should use positive sign, and the magnitude, which is V2 dA. Okay, now what we have is minus Rx equals minus rho V1 square A1 minus rho V2 square cosine of 30 A2. We have the area, since we know that the jet the jet cross section is a circle with a diameter of 2 inches. So, and we know that A1 equals A2. So we know that, A1 equals A2 equals pi over 4 d square, and we know that d is 2 inches. But we don't know anything about the velocity. That's where this stagnation tube comes in, and we should use it. But how we can use this? As you know, the stagnation tube here can calculate the stagnation pressure. Here P is static pressure, one over 2 rho V square over 2 is dynamic pressure, and if we add them together, the total value, which is P plus 1 over 2 rho V square over 2, which is known by PS or PT, stagnation pressure, total pressure, is the stagnation pressure or total pressure. So when you have this stagnation tube, it means that the pressure here, the pressure which is calculated by this stagnation tube is PT. So here we have PT, and I think this is water. This distance is 0.7. Oh, sorry. Seven inches. So we can use the manometer equation. We start from point A and move towards this opening here. Since we have air in this tube, you know that the pressure here is PT. There is no change in pressure. So PT, which is P1 here, is 0.1, is the control surface 1. What we have here is CS1 because the pressure doesn't change from this point to this point. The place that we have control surface 1. So P1 plus 1 over 2 density of air V1 square over 2. If we move upward from this point to this point, we move upward, so we should subtract the pressure minus gamma of water times H, which is 7 inches. We reach point B, which is atmospheric pressure. P equals PATM. But we know that the static pressure here at this area is also atmospheric pressure because we have atmosphere there. So actually P1 is PATM, which is 0. Why? Because we are working with gauge pressure. So this is 0, and also the other side. From this we can find that V1 equals 2 gamma of water times H over rho density of air, square root of this. Now we have V1, and since we know that V1 equals V2, why? Because we have conservation of mass, so m.1 equals m.2, or since density of air is constant, Q1 equals Q2. So A1 V1 equals A2 V2, and since A1 equals A2, V1 equals V2. Okay, now we have V velocity. Now we can solve equation 1. So if we put the values, Rx equals rho v1 square times a1 rho rho is density of air v1 square 2 gamma h rho air times a1 plus the same rho v2 square 2 gamma h rho air cosine of 30 a2, which is equal to a1. So Rx equals 2 gamma h 1 plus cosine of 30 times area, which is pi d square over 4. Now the values are x equals 2 times gamma 62.4 pounds per cubic feet times h 7 over 12 feet times 1 plus cosine of 30 times pi over 4 2 over 12 feet square. So Rx equals 2.96 pounds. Oh, sorry. No, it's okay. Now you can solve the problem. Let's jump to the next problem number 66. Here we have a mesh screen, variable mesh screen produces a linear and axisymmetric velocity profile. This is the linear profile and axisymmetric, since we have a pipe here. As indicated in the figure below, in the airflow, so we have air through a 2 feet diameter circular cross-sectional duct. So we have a circular duct with diameter of 2 feet. The static pressures upstream and downstream of the screen are 0.2 and 0.15 psi. So we have the pressure before and after this mesh screen and are uniformly distributed over the flow cross-sectional area, okay, neglecting the force exerted by the duct wall, which means on the flowing air, which means friction due to viscosity. Calculate the screen drag force. Okay, so first step is to define the control volume, for example something like this. So this is the control volume. We have inflow. I show it by this vector. V1, which is 100 feet per second. Since we have pressure and we are solving an internal flow, we have a force P1A1. So here we have P1. And also we have this force P2A2. Don't forget, pressure forces are normal to the control surface and towards the control volume. So here is CS1, here is CS2, and we have outflow, but the velocity is not constant. It's a function of radius. Don't forget, this is a pipe. So if you look at the pipe from right view, you will see this, and we have to use the integral because the velocity is a function of r. Actually, and it's linear. Actually, at r equals 0, if we define r, this one, velocity v2 is 0, and at r equals r, v2 equals vmax, I think. Yes, vmax. So from this you can find the velocity. When we know the velocity is a linear function, it means that it's, for example, c1 r plus c2. If you do the math, you will see that v2 equals vmax times r divided by the outer radius, which is 1 feet, I think. Okay, we know v2, v1, and for the pressure, so we consider this x and y axis, and we can solve it now. So the summation of forces in x direction equals the change of momentum inside control volume plus c, the exchange of momentum v dot n dA. So it's 0 since we are working at the steady state. And we have, I forgot to include the force, the drag force, which is Rx. This is the drag force acts on the mesh screen. So we have three forces, P1A1 minus Rx minus P2A2. Rx and P2A2 are in the opposite direction compared to x, and it's equal to, we have two control surfaces, where control surface 1 we have rho v1, which is constant, and it's parallel to x. v1 v dot n equals minus v1 because we have inflow, dA plus over control surface 2 rho v2. v2 is parallel to x, but it's not constant. It's vmax r over r. v dot n actually, since we have an outflow, it's equal to the magnitude with positive sign. So vmax r over r dA. What is dA? If you look at the cross-sectional view, you have to use this differential element. This is r. Here is dr. So dA equals 2 pi r, the circumference of the inner circle, times the thickness, dr. And now we can continue. So P1A1 minus Rx minus P2A2 equals minus rho V1 square A1. In this integral, rho and V are constant, so you can solve the integral easily. For the second integral, you have to do the integral. We have rho Vmax 2 pi dA is 2 pi r dr. So we have 2 pi and r square here. This Vmax is also squared. And now we have 1, 2, 3 times r to the power 3 dr. I hope I do it correctly. Okay. And now we want to find Vmax because we need it. How we should do it? We know that we have conservation of mass, so Q1 equals Q2. So Q1 equals V1 A1. Q2 is integral of V2 dA equals integral of Vmax r over r times 2 pi r dr. So V1, which is V1, and the area is pi d square over 4 equals the integral of, or let me do this, Vmax 2 pi, Vmax and r are constants. We can bring them out, and inside the integral we have r square dr. So it's equal to 2 pi Vmax over r from 0 to r. All these integrals are from 0 to r. And r3 over 3. Integral of r square is r to the power 3 over 3 from 0 to r. Now we can find Vmax. Vmax equals V1 pi. No, we don't have that. This pi with this pi. And I think it's okay. So we don't have pi. V1 d1 square. This is d1. R, this one, divided by r to the power 3 times 4, and here we have 3. And we have another 2 here. So Vmax can be found as okay, d square equals 4r square. So these are cancelled, and this one, so Vmax equals 3 over 2 V1 equals 150 feet per second, because we know V1. Now we have everything. We can solve the equation. So equation 1, P1, A1, and we know A, which is pi d1 square over 4 minus Rx minus P2 times P2 times pi d2 square over 4 equals minus rho v1 square pi d1 square over 4 plus the integral. You can bring out the constants, rho v2 v square v max square actually times 2 pi divided by r square integral of r to the power 3 from 0 to r dr. Yes, that's it. And you know that this equals r to the power 4 over 4 from 0 to r equals r to the power 4 over 4. Now you have everything, and you can find r1, rx. I think you can do the math. You know P1 is 0.2 psi, pounds per inch square. Don't forget to convert it, 144 inches square over feet square. P2 is 0.1, you have to do the same. D1 equals D2 equals 2 feet. V1 is 100 feet per second. We have Vmax, we know R, and we know rho. The density of the air yes, is 0.00238 slugs per cubic feet. Now you can do the math, and Rx would be 13.3 pounds. I think doing the math and the calculation is the easiest part, so I leave it for you. And this is the last question. The last problem number 70. Here we have a Pelton wheel. A Pelton wheel vane directs a horizontal, circular, cross-sectional jet of water symmetrically. So first, we have a 3D Pelton wheel here. Some of the students make this mistake and think it has two outlets. No, it's a symmetrical. So basically it's a 3D and we have only one outlet here, but this is symmetrical. Okay, the jet leaves the nozzle with a velocity of 100 feet per second. So the inlet velocity is 100 feet per second. Determine the x direction component of anchoring force required to hold the vane stationary. So this jet impinges the wheel, the vane, and we want to keep the vane in place at part A, and we want to find the force we needed. In part B, if the vane speed is 10 feet per second, what would be the force magnitude? Okay, and we have this assumption that the fluid speed magnitude remains constant along the vane surface. So we have at the inlet we have 100 feet per second, and at the outlet we have again 100 feet per second, but it's inclined and we have to be careful. So the first step is to draw the control volume. So this is the control volume we have from here, or you can move it, for example, here, closer to the vane. Follow the flow. Okay, let me zoom in and draw it. We're using solid line. Go with the flow and then perpendicular to inlet or outlet. And here is the surface, the wall of the vane. Okay, everything is fine, I think. So this is the control volume. Here we have Rx, the force. We have inflow. We have outflow. Remember and be careful, this is one outlet. It's a symmetrical. We have a 3D Pelton vane. Okay, let's solve part A. Okay, what do we need? The second step is to define x-axis. And here we have V1, here we have V2. So let's write down the linear momentum equation in x direction, because the force Rx is in x direction. So the summation of forces equal to the change of momentum inside the control volume, which is 0. We are working at a steady state, plus integral of rho Vx V dot n dA. We have two control surfaces, CS1, CS2, and we only have one force. So minus Rx, because Rx is in the opposite direction, equals, for control surface 1, rho Vx is V1 and V dot n is minus V1. Why? Because we have inlet dA. For control surface 2, rho V2x. Okay, if this is V2, the angle is 45. So this component V2x equals V2 cosine of 45 degrees. Okay, rho, but be careful, it's in the opposite direction. So minus V2 cosine of 45 degrees. V dot n, since we have outlet, is positive. V2 and the magnitude. There is no need to find the component of velocity in x. It's the total magnitude, dA. So what we have is minus Rx equals minus rho V1 A1 plus, actually minus rho V2 cosine of 45 degrees times V2 A2. Okay, the fluid speed magnitude remains constant. So V1 equals V2. We know that. And since V1 equals V2, we know that Q is constant. So A1 V1 equals A2 V2. Since V1 equals V2, it means that A1 equals A2 because we don't have A2 and we can't calculate A2. But now we know A1 equals A2. So from these we can find that Rx equals rho V1 A1, which is pi d1 square over 4. So this is A1, and instead of A2 we have A1, and instead of V2 we have V1 because they are equal. And if we factor out this, we will have V1 plus V1 cosine of 45 degrees. Actually, this is also V1. Now we can find Rx. Rx equals 1.94 slugs per cubic feet times pi times V1, 100 feet per second times pi d1, which is 1 inch, 1 over 12 feet square over 4 times V1 100 plus 100 cosine of 45 degrees. And we should do the conversion. 1 pound is equal to 1 slug feet over second square. So Rx equals 181 pounds in the first part. For the second part, we should consider that the control volume is moving with a constant velocity of 10 feet per second. When we have a moving control volume in steady state, so moving CV, and we have steady state condition, we can use the summation of forces. This formula, the summation of forces equals integral of W rho W dot N. Actually it's dA. It's like the general form, but we don't have the first part, and instead of V, we are working with W. W is the relative velocity, so nothing changed. Oh, this is CS. You just need to find the relative velocity and use it in your calculations. So when you have let me draw this again. When you have this control volume and you have this inflow V1 while the control volume itself is moving with C, for example, which is 10 feet per second. C is the velocity of control volume. The relative velocity W equals the velocity we have minus the velocity of the control volume. So here it's easy. W equals 100 feet per second minus 10 feet per second. Remember, this is x direction and they are both parallel and in the same direction as the x-axis. If, for example, you had this situation, C was towards the left, then for this, W would be V1 minus C. You know, these are vectors, and C is in the opposite direction in this hypothetical situation. So you will end up with W equals 100 feet per second plus, actually minus 10 feet per second, 110 feet per second. Why? Because C is in the opposite direction, so it's minus, it's negative, and you will have that. But in our problem, it's equal to 90 feet per second. So everything is the same as part A. The only thing that changes is W, is the velocity. So Rx equals rho V1 pi D1 square rho V1 pi D1 square over 4. Sorry, this is W. So pi D1 square over 4 W1 times W1 plus W1 cosine of 45 degrees. And now you can do this calculation exactly like this, but instead of these 100s, you will have 90. So in this situation, Rx equals 146 pounds instead of 181. So the force we need is decreased. That's it. It's the end of this tutorial, this episode. I hope you've enjoyed it. This part, of course, is a bit challenging. Don't forget to introduce us to your friends, like these videos, share these videos, and subscribe to the channel. Thank you for watching this video. Until the next one, take care of yourselves and bye bye.